Good morning or good afternoon. Welcome to N39, our beginning of solutions or properties of solutions. Take a moment and copy the target down. I'll pause. All right, let's move on. So this chart, don't need to copy it. You've seen this before. We used it a lot early on with chemical, physical changes and all of that matter. But for this one, with solutions, we are focusing on one single box, and it is homogeneous mixtures. All solutions are homogeneous mixtures. Any questions on that one? Alrighty then. So all of our solutions are made up of two parts. You have the solute and the solvent. Solute is always that thing that you are dissolving in the solution. So putting salt in water, sugar in soda drinks that there's way too much of. Public service announcement, don't drink soda. Carbon dioxide also in soda, which leads to carbonic acid, which is what helps, eat away at the enamel on your teeth. So all in all, soda is bad. Water is good. Go with that. However, the solvent is the thing that you're dissolving something into. Water in salt water. Water is our universal solvent. Now, there is water in soda. No, this does not mean soda is good for you, but there is water in it. So again, solute and solvent are two parts. You must have both in order to have a solution. So our solution, as we just said, is solute and solvent combined to make this lovely solution. So salt water or soda, they are, by definition, solutions. Don't drink soda. I don't know if you've heard me say that before. Then this brings us to solubility. Now, some things are more soluble than others when you make a solution. Ultimately, solubility is the amount of solute that can be dissolved at any given temperature. Solubility also does depend on the amount of solvent that you have. If you ever made, country time lemonade or Kool-Aid, invariably you have some solid still sitting at the bottom of your pitcher, even though you've followed the directions, you've mixed everything. It's just not all of it is completely soluble. It just doesn't work out that way, and that's fine. Questions? Alrighty then. So types of solutions, do not copy this down. There is a link to it on the one-stop shop if you've not seen it yet. Good one to print out, 50%, maybe 75% size, paste it into your notes. But again, multiple types of solution, gaseous solutions, liquid solutions, solid solutions. Again, giving you what the solute is, what the solvent is, and some examples. So please take a look at this when you get a chance and or print it out, put it into your notes. It'll be very, very helpful. All right. So saturation, you may have heard this term before. Now, a saturated solution, vocab word, maximum amount of solute is dissolved. Now, this does depend on the amount of solvent that is present, as well as temperature. Again, the example I gave of making country time lemonade or Kool-Aid or any one of those powdered drinks, having stuff left over at the very, very bottom means that you have made a saturated solution and no more solute can actually dissolve. That's our saturated solution. Brings us to unsaturated solution. So less than the maximum amount of solute dissolve. So let's say you make Kool-Aid or country time lemonade. You use too much water. Everything dissolves. Nothing at the bottom. However, doesn't really taste that great. It does taste watery or less lemony because you have an unsaturated solution. You've not dissolved the maximum amount based on the amount of solvent present, assuming temperature is constant. Lastly, we have a super saturated solution. Again, more than the maximum amount of solute dissolved. The only way to make a super saturated solution is by increasing the temperature. So you have your set amount of solvent, you've added your solute, and once you start heating it up, you're then able to add more solute, and you can get more and more to actually dissolve. Yes, there is a point in supersaturated. There is no infinite amount you can add. You will reach a maximum. The point is with supersaturated, you have dissolved more than a saturated solution. Any questions on these three? Okay, the YouTube video link here, again, you can get access to it with the PDF version on my website, but hopefully I put it here, and we're going to see if it actually works.
The flask contains a supersaturated solution of sodium acetate in water. A small crystal of sodium acetate will be added to the solution. Focus your attention on the portion of the solution to which the crystal is added. Here is the process again in slow motion.
All right, so before I move on, so what you saw there, just to give you a heads up with that lovely demonstration, was they had made a supersaturated solution. So very, very little amount of solvent and a heck of a lot of solute. So much so that dropping a single grain of the solute, the sodium acetate, it caused a disturbance in that solution, and all of the solid precipitated out, and the whole thing turned solid. Usually when you make that solution, you're using like 3 or 4, more like maybe 10 milliliters of water to like 25 or 30 grams of sodium acetate, heat it up, and you could have flicked it with your finger and it would have all come out of solution. But with that example, as you saw, they took one single grain of sodium acetate as a solid. The minute it touched the solution, everything came out. Questions on that one? Alrighty then. So moving on to colloids. These ones are not really solutions. They are a little tricky, if you will. Basically, when large particles are suspended in a substance. So when we mean large, or 5 to 200 nanometers. Remember, nano, 10 to the minus 9 meters. It is considered big. So these are pretty big particles compared to obviously much, much smaller. For example, fat molecules suspended in milk, whipped cream, butter, mayonnaise. Those are representations of colloids. A lot of you may drink milk and put whipped cream on an ice cream sundae. Butter your toast, mayonnaise. I'm not sure why you would drink mayonnaise. It's kind of right there with soda. You shouldn't do it. But again, public service announcement from me. That's all. Air bubbles suspended in foam rubbers. So again, another example of a colloid. Color particles suspended in glass, paint, or cosmetics. So again, all these things, some you may have experience with seeing firsthand or pictures of it. But again, they're just, a different type of solution, but not really a solution. Fog, smoke, clouds, aerosols, all kind of represent colloids. Questions on this one? Alrighty then. All right, coming back to solubility. So temperature and pressure can affect solubility, especially when you're dealing with solids, liquids, and gases. gases and solids are affected differently sometimes, depending on what you're doing. So graphically, usually solubility tends to increase with temperature. So here's our solids. Temperature goes up, solubility tends to go up. This is not an always thing. From a gas perspective, when you increase temperature, solubility actually goes down. We know what gas molecules tend to do when you heat them up. They move around more. They go faster. Less likely for them to create bonds with a solvent and quote unquote dissolve. Pressure of gases, actually, the solubility increases when you apply greater pressure above. So it's like you're pushing gas into it. So again, take sodas, carbonation. You're forcing carbon dioxide into the solution. By applying a greater pressure, you get more carbon dioxide in to your solution. On the flip side, if you ever open up a soda, which you're not drinking, so I don't know how you do this, if you pour a room temperature soda versus pouring a cold soda over ice into a glass, the room temperature one tends to have way more foamy stuff, whereas the refrigerated one is going to have less foamy stuff. So maybe the next time you get flavored sparkling water that has some carbonation in it, and keep one in the fridge overnight, keep one on the counter overnight, and then pour them into glasses with ice, and you'll see that difference. Questions on this? Okay. Continuing with solubility, we get our solubility table. Now, you can see that graphically you can read the chart. We have temperature on the x-axis, and if you notice on the y-axis, solubility is in grams of solute per 100 milliliters of water. So that's kind of the big thing with solubility, is it's, how many grams of this solute per a known amount of water. That y-axis could change a little bit, could be per liter, could be 50 milliliters. You go with what the graph says. Here's looking at gases. So methane, oxygen, carbon dioxide, nitrogen, helium. All gases, in 10 to the minus 3 molarity is solubilities could be represented in molarity. So as temperature goes up, you can see how the solubility goes down of all of these gases, which we already showed with a graph last time. Back to the graph on the left, it doesn't show it, but there are some curves that actually have a negative slope. When you increase the temperature, the solid becomes less soluble. I know all of these ones do show the opposite of that, but there are solids that actually, for some reason, just their properties, their bonding, heated up, they come out of solution. Questions on either of these graphs? Alrighty then. So, with solubility, we can identify saturation points using the curve. And that's the cool thing in order to identify what's going on. So, for example, when you're on the line, so based on your y-axis and your x-axis, when you're on the line, you are a saturated solution. If you are above the line, you are a supersaturated solution. And when you are below the line, you are a unsaturated solution. So those are kind of key points there. If I were to give you a graph and ask you, at this temperature and this amount, is the solution saturated, unsaturated, or supersaturated? So all based on the line, above the line, or below the line. Questions? Alrighty then. Now, solubility rules. Now, your solubility curve is going to be more accurate than this general chart, but this is one that you guys are going to really need to start paying attention to. If you're taking AP Chem, you're going to have to know this. You will not be given this. You have to know it. For honors, I believe if we want you to use it, then we'll provide it to you. So it's pretty self-explanatory. You take a solid solute, some ionic compound, a salt, and you look at the ions involved, either the anion or the cation. So, for example, if you take anything column 1, so lithium sulfate or potassium carbonate or ammonium nitrate, all those things, column 1, they're in this first column, they're always soluble. So column 1 metals with any other anion will always be soluble. So a little mnemonic device there on the right, AAA, the car insurance company, and CNP. As you can see, it follows with the names of those ions. Generally soluble, chlorine, bromine, and iodine. So AP and honors courses. Chlorine, bromine, and iodine are soluble with anything except silver, lead, mercury. AP and honors courses, A for silver, P for lead, and the H for mercury. So it's a little device to help you memorize what's going on. So to use the chart, as I think we've seen this before when we were doing double replacement reactions, we wanted to use it. So keep in mind, know how to use this chart, and it could come up again. Questions? Alrighty then. So dissolving. What's going on here? When molecules of solute are surrounded by molecules of solvent, and they're pulled apart from other solute molecules. One keyword could be solvation or hydration are keywords that are used to help describe the dissolving process. This is in contrast to dissociate. Okay, so to dissociate, when an ionic compound has its ionic bonds disrupted by solvent molecules and breaks into its individual ions. So dissolving is different than to dissociate. Yes, it is similar at the end result, because when an ionic compound breaks apart, it then is eventually surrounded by those molecules. So dissociate just is meaning you are breaking the ionic compound, the lattice structure, apart. To dissolve is when those ions are broken from their lattice structure, they are then surrounded by solvent molecules. So kind of two different processes, interestingly happening simultaneously. Questions on this difference? Alrighty then. So electrolytes. Most of you are thinking Gatorade. Ionic solutes that dissociate, they come apart, they form ions in solution, are all electrolytes. If it's insoluble, it is a non-electrolyte. It does not break apart. So for example, table salt breaks into ions, it is an electrolyte. They do conduct electricity because of the charged particles for the electrons to move between. So you need movable charge to conduct electricity. Electrolytes, yes, Gatorade, Powerade, will conduct electricity. Questions on electrolytes? All right. Which brings us again to non-electrolytes, as I had mentioned. Covalent solutes that do not dissociate, or ionic solutes that are insoluble according to solubility rules, but they can still potentially dissolve in a solvent. So sugar. Sugar dissolves in water because of hydrogen bonding with sugar and H2O, but it does not dissociate or dissolve. It does not dissociate. It dissolves but not dissociate. Therefore, it cannot conduct electricity. So here's glucose as a solid becoming glucose as aqueous. You don't have two different ions. Nothing is charged. Questions? Alrighty then. So which is dissolving and which is dissociating if we look at our little pictures here. Take a moment. Alrighty then. So the left diagram should be having dissociate, the charged lattice structure of the plus and minus, but it's also dissolving because the plus and minus are being surrounded by water molecules. The right-hand diagram, there's nothing dissociating. It's not coming apart, but the water molecules could be forming an attraction around there, so could be also dissolving. Questions on this one? So there's our dissociating, but also dissolving, and this one is just dissolving. Woohoo! All right, the dissolving process. We have a heat of solution. The amount of energy it takes for this to happen can be exo or endothermic. Easy enough, we're familiar with that. But at the end of the day, it's like dissolves like. Things that have the similar bonding characteristics, similar IMFs within their molecules, they are going to dissolve within each other. If they are different, they're not going to dissolve with each other. Questions on this? Alrighty then. So, increasing dissolution, or how fast something dissolves. Solids, we know, will increase their dissolving or dissolution. When you increase temperature, more collisions, more is going on. More is going on. Stir it to expose more surface area. Put it in a blender. Stir with a fork or a spoon. Same idea. Gets more things moving around. Crush it up to create more surface area. Granulated sugar versus a sugar cube. Granulated will dissolve faster. From a gases perspective, decrease the temperature. It's going to work better. Increase the pressure. It's going to work better. Force more into the solvent. So, just an example of increasing pressure. P1 versus P2, you can see there are more molecules that are in the solution. Any questions on this? Alrighty then. Thank you very much. Until next time, later.